Hey everyone, my name is Jad Silbak, and this talk is going to be about detecting and correcting computationally bounded errors, a simple construction under minimum assumptions, and this is a joint work with Daniel Wicks. Good. The focus of this talk is going to be about the intersection between coding theory and cryptography, and we all know that, of course, coding theory is extremely important for theoretical computer science, and this, of course, is true also for crypto. I won't say all the various applications we have for coding theory, but the focus of this talk is going to be about the other direction, and that is to say, how can we use cryptography to improve coding theory? Now, the setup we should keep in mind is that we have some message M. We wish to send this message through some noisy channel, and to do so, we're going to first encode this message using some encoding function, adding redundancy into the message. So hopefully now when we send it through this noisy channel that induces some errors, the other party can apply a decoding algorithm on this damaged code word and hopefully recover the original message, or output both in case of error detection. Now, the ratio between the length of the message and the length of the encoding is, of course, the rate of the code, and we want this to be as large as possible because this would mean that we didn't add a lot of redundancy and the code is efficient. And finally, we're going to use Q to denote the alphabet size and N to denote the length of the message. Good. Now, usually coding theory is studied in the information theoretical setup. And by this I mean Hamming channels. Now, Hamming channels are channels that can change any PN symbols in the encoding. So the only limitation on the channel is the fraction of symbols that it can change. And this is an adversary in the full sense, right? It looks at the encoding and then decides which kind of error it wants to induce. And of course, the rate of these channels is determined fully by the distance between every two code words, or the minimum distance of the code. And one of the most fundamental and basic bounds in terms of rate and distance, of course, is the singleton bound. And the singleton bound says that you can't detect more than 1 minus the rate, fractions of errors, of course, and you can't correct more than 1 minus the rate over 2. Now, this bound is also tight for large alphabet. However, it makes sense also to consider intermediate classes of channels, or a relaxation of the information theoretical adversary, and by this I mean computationally bounded channels. And in fact, Lipton himself already considered such channels that have two limitations. The first is that they are going to induce at most PN errors, and that is to say they are a subset of the usual Hamming channels. And the second is that they are drawn from some computationally bounded channel. Right? So for example, think of PPT adversaries, branching programs, SE0, etc. And the rationale behind this approach is that essentially all errors that arise from natural processes can also be simulated by such computational process. And as such, it makes sense for us to consider this relaxation because it mimics or it simulates real-life behavior. In this talk, we're going to consider probabilistic polytime channels, or PPT for short. And by this I mean that we're going to consider algorithms that run in some polynomial time and induce at most PN errors. And the take-home message of this talk is that under minimum cryptographic assumptions, we are able to construct codes for PPT adversaries, or for computationally bounded adversaries, if you want, under minimum assumptions and without any setup, achieving a better rate than what's possible for Hamming. Okay, so you should think of this as being or having an adversary that is computationally bounded and has a limitation on the amount of error it can induce. But other than that, this is exactly the setup you would want or expect from coding theory. Okay, and we're not the first to consider this. So let me mention out some of previous results for coding for computationally bounded channels. And there are a few distinctions I want to highlight. First is that there is a line of work that considered constructing codes for PPT adversaries with some trusted setup, starting with Lipton himself that considered shared secret keys, and follow-up work by Mikali et al. That considered public key infrastructure. So assuming public key infrastructure, they were able to get better codes for PPT. And maybe the recent result, or most relevant result, is the recent result by Grossman et al. That assumed CRS and strong non-standard assumptions they were able to get better codes for PPT. So these are kind of assumptions that are assumed to get PPT results. All of them involve some kind of trusted setup. Another line of work that is also relevant is a more complexity-oriented line of work started by Goswami and Smith and later developed or built on by ShLTL and myself. And this line of work assumes more, or has a caveat in that we are assuming that the complexity of the code itself is more than the channel. So if you think about the channel as being some n to the c size channel or adversary, then it kind of implies that the runtime of the encoding and decoding should be more than the runtime of the channel. So this is a major caveat, and of course this means that we don't get codes for PPT. We get for weaker classes of channels. However, the offside of this is that we're able to get this from weaker assumptions or non-cryptographic assumptions. Good. So these are like two lines of work. One of them assumes kind of a very strong assumptions in the form of trusted setups and maybe non-standard assumptions. And the other is a weaker kind of assumptions, or maybe without any assumptions. But these kinds of work are non-cryptographic in design, and they don't apply for any PPT adversary. However, I've cheated a bit, and there is one subtlety that we have yet to address, and that is, suppose you have a code that is good for size n non-uniform channels. Okay, so we also want to be able to deal with non-uniformity. So let's suppose we have a non-uniform adversary that has very little non-uniformity. Let's say just n bits of non-uniformity. So if you think about it, this channel is also good for or against Hamming channels. So if you have a code that is good for size n non-uniform channels, then it's also good for Hamming channels. So we didn't do anything by this relaxation. So relaxing to this computationally bounded setup did not give us anything. And the reason is, well, we can use this non-uniformity to hard code this error pattern that would induce an error inside the adversary, right? So the adversary could be just hard coded with this error pattern that we know that should imply errors, right? So if there are two code words that are too close to each other, that is to say the code is not good for Hamming, then just by hard coding this non-uniform distance between these two code words, we're able to induce a decoding error, right? We are able to push one code word toward the vicinity of the other, and this would lead us to decoding error. So there is a problem, right? This problem is that this relaxation of the adversary to this computationally to be computationally bounded did not give us anything if we're willing to assume non-uniformity, or we want to deal with non-uniformity. However, the solution to this is that we're going to now assume randomized codes. And for randomized codes, the encoding is going to be, or going to have access to randomness, and the decoding is only going to succeed with high probability. So we're going to get success with high probability, and the encoding is going to be randomized. However, given these two things, we are now able to leverage this computational restriction on the channel to probably or hopefully get codes with better rates than what's possible for Hamming channels or for information theoretical adversaries. Good. So let's now retell the story of coding theory, just this time for randomized codes. So again, we have the message M. We wish to send this message through the channel. We encode this message, but this time we give randomness to the encoding function, and R here is a uniformly chosen string. We send it through this noisy channel. To be specific, this noisy channel is now a PPT algorithm, and this noisy channel induces at most p errors. The other party applies its decoding algorithm on this damaged code word and hopefully recover the original message. Crucially though, the decoder does not receive this randomness. This means that there is no setup involved in this. Good. Formally, this means that a randomized code is a pair of encoding and decoding algorithms such that for every PPT adversary A, if this adversary first chooses the message M, then we choose some randomness R, we encode the message using this randomness R, and then the adversary that is stateful sees the message and this encoding, figures out some closed code or a string such that this string is at most p distance from this encoding, and it should hold that the probability that the decoding of this string equals the message is high. Okay, or for the case of detection is that either it outputs the original message or it outputs both with all but negligible probability. So this is our definition for randomized codes. Again, this is a straightforward algorithm that first chooses a message, the randomness is then chosen. Afterwards, it can choose the error pattern if you want. Okay. Alternatively, we have a stronger definition, which we call self-seeded codes. Again, this definition is a more adaptive notion of security for coding theory. And in this definition, first the randomness is chosen and is given to the adversary. So the adversary does even know the randomness at this point. Okay, we're not hiding the randomness. Afterwards, adversary can choose the message and the error pattern it wants to induce. Okay, so Z or Z, the code, the string that the other party receives, is at most p distance from the original code word. Okay. Note here that this is an adaptive notion, and this stronger notion implies the randomized notion. So self-seeded codes are a stronger variant of randomized codes, and they give you an adaptive notion of security. Great. So now that we have a formal definition, we can formally state our results. And our main result, or our first result, is that assuming one-way functions, we are able to get randomized codes for PPT channels, okay, with detection that is obviously optimal in the sense that we can get rate 1 and detection up to 1. And this approximation is some constant, right? You can choose this constant to be as small as you want. And we can also get correction with rate R and P1 minus R, which matches the list decoding capacity and the distance, but does not match the usual error correcting capacity. And the one caveat of this result is that this result only holds for large constant alphabet, and the constant depends on how close you want to be to this bound. So if you want to be very close to the bound, in the sense that you want P to be as close as possible to 1 minus R, then the alphabet will grow accordingly. Otherwise, you can choose the constant in the alphabet size to be small. Okay, but it can be 2, for example. So let me emphasize that there is no trusted setup here. So this result has no trusted setup. It's a very simple construction, and hopefully I'll be able to show to give a proof sketch for it. And as I stated a moment ago, this is strictly better than what's possible information theoretically. Okay, so it's obviously true for the detection, where we can get rate 1 and detect almost 1 errors. But this is also true for the correction. And as we can see here, this is assuming one-way function. We get the randomized codes, which is the weaker notion we discussed before. But if we're willing to assume, instead of assuming one-way functions, we're assuming collision resistance hash functions, then we get a stronger notion of self-seeded codes. So we get this result for both of them with the same parameters, with the same restrictions. Essentially, it's a unified construction. You can either plug in one-way functions or CRH, and you can get equivalently either a randomized code or a self-seeded code. That is to say, you get the adaptive notion or the non-adaptive notion. Perfect. So let me compare this to what we know about the singleton bound. So if you compare this result or a result to the singleton bound, which is the best possible for large alphabet, right? It's actually achievable for a large alphabet. And we know that P is strictly less than 1 minus the rate. And we know that P is also strictly 1 minus the rate over 2. Okay. So if you compare it to our result, then it's a very big gain for the detection, but it's also quite a big gain for the correction. Now, the second result in our paper is that suppose you have a code or a randomized code that is better than what's possible for the singleton bound, as is the case, of course, for our result, but even a bit less than what you get for the result. Our result is quite good, but even anything that is actually better than the singleton bound would imply one-way functions. So any randomized codes with any parameters, either detection or correction, that beat the singleton bound will imply one-way functions. And this is also true for the self-seeded codes. So if you had the self-seeded code that is in any way better or bypasses the singleton bound, then it implies collision resistance hash functions. Okay, so the results are tight. These primitives imply these results, and anything non-trivial would imply this primitive. So with that out of the way, let me try to give you a high-level idea on how we achieve this result. Okay, so let's start with a toy example in which the error correction we want to achieve is for some exponential size alphabet. And let's start by describing the encoding function. So the encoding function is going to use some hash function, and this is quite similar to other works in this regard. However, unlike other works, we don't use or we don't need any trusted setup. And the construction itself is very simple, and you'll see in a minute. So again, we have this hash function, and you have this randomness as an input. You have the message, and you use this randomness as the seed for the hash. And we're going to set sigma here to be the seed of the hash plus plus applying the hash on the message with the seed. Okay, so h of r of m. Good. Now let me write it here. So we have the message and the seed, and the first thing we're going to do is that we're going to split the message into blocks of w size. So each block here is going to be of size w. Okay, so this is, we're not doing anything at the moment. We just took the message, we split it to blocks of size w. Okay, and the thing we're going to do is very simple. We're just going to take this hash, and we're going to append it into each one of these rows, right? So each block is going to be appended with one of these sigmas. Now, you should think of each sigma, or each block, or each row here, as being a single symbol in a higher alphabet code. So M3 sigma or M2 sigma together, or like M3 sigma as a whole, define a single symbol, and this symbol is going to be of a higher alphabet size. And whenever we want to say or want to get a randomized code, or want to get randomized codes, we're going to use universal one-way hash functions, which are known to be implied or quite easily implied by one-way functions. And to get the self-seeded codes, we're just going to use, instead of having universal one-way hash functions, we're going to use collision resistance hash functions. Okay, so we get the notion of randomized and self-seeded codes depending on the hash we choose here. But that's it. This is the construction, right? This is the encoding, in which actually does give you this quite simple and maybe trivial in some sense, or easy to see, a code that gives you detection quite easily. And the detection here is very good in a sense that you will have to change all the bits, right? So you can detect n-1 errors up to the tolerance of almost 1, right? So if I changed everything here, or all symbols except one of them, then you're still able to detect, because you can see that they're not the same. You can look at sigma and see that it's not the same. And here we're using the fact that the hash itself is kind of committing to the message we're using. So we use this hash, and since this hash is shared across all of these symbols, if you change any of the symbols here, then this would mean that you also had to change the hash. Okay. Now the rate of the code is just going to be the ratio between the length of the message block, which is w by design, right, over w plus sigma. So by choosing w to be sufficiently large, or sufficiently larger than sigma, we can take this to be as close as we want to 1. So the rate can be close to 1. Perfect. So this is a very easy way in which we're able to get encoding and decoding where the alphabet is large. Now, to extend this to smaller alphabet, so let's see what we can do. So as we said before, we want constant alphabet. So the first observation is that we can't really now append sigma as is to each block, right? Because if we just appended it, then this implies that the size of each symbol is too large, and we want to go to constant size. So instead of having this like a part here for the sigma be seen as a, let's say, a repetition code, we can just use another code or a better code. So instead of just appending sigma to each block, we're going to first apply some encoding algorithm on this sigma. And this, because sigma is small, we can have a code that has a small rate, quite close to 0, but with very high distance, like quite close to 1, right? So we can, and this is quite easily achieved by a lot of constructions. You can probably come up with it yourself, and you can get a constant size alphabet for it. So you can get a constant size alphabet with a code that has rate almost 0 and achieves a distance almost 1. And what we're going to do is that after encoding sigma, we're going to put each symbol of this code inside the appropriate row, right? So changing what we had before, what we need to do, what we need to put now is that after encoding the hash or the sigma, we are going to take the first symbol and attach it to the ith block. And the decoding is going to change appropriately, and that is to say we're going to first try to recover the hash or to recover sigma. And if we're not able to recover it, that is, when we try to recover, we see that this is not a correct code word, then we just abort. Otherwise, if we're able to recover, then this kind of implies by the distance of this by the distance on the sigma part, this implies that you were not able to find any, or you had to change a lot of code words, a lot of symbols to actually change it. So if the adversity does not change or changes less than half or changes less than 1, then you're able to, or you are able to know that there was some tampering. And this is to say that after recovering the message, or after recovering sigma, sorry, you can check consistency with the message, and if it's not consistent, you can just abort. Okay. Now again, the error tolerance here is also close to 1, and the rate, because now we can take sigma here, or sorry, we can take each of the c tildes to be of constant size. We only need w to be of sufficiently high constant. So we can choose w to be sufficiently high constants depending on ci, and we get the rate to be like close to 1 appropriately. Okay, good. So now we have this, we're able to deal with the error correction, error detection, and we want to finally get rid of the last caveat, and instead of detection, we want to get correction. And the trick here, or the general strategy that was used previously by prior results, is that we're going to go from list decoding to unique decoding and inherent essentially the rate of the list decoding. And the intuition here is that if the adversary is able to produce a list that contains more than one consistent message that is consistent with the hash, then this would imply that the adversary is able to find a collision for this single hash, because the hash does not change. But if the hash is not changed, then this also only implies that you're able to find two messages with the same seed of the hash that map to the same output, or the same sigma. So we're going to encode this using list decodable code. And for the sake of this talk, let's just say we're going to use the Kursmami Rudra code that has a rate that is optimal, 1 minus r, and has constant size alphabet for list decoding. Okay, and we're going to change the message. Instead of like just partitioning the message, we're going to encode it using this list decodable code. And after encoding it using this list decodable code, we're going to append each part of it as is described in this image. Now, the decoding is going to first try to uniquely decode the control part, or the sigma part, after which you have a candidate, some seed and y, and now you check inside the list decoding, right? So you perform a list decoding on the data part, and after performing a list decoding on the data part, you check each message, and you output the only message that should exist, such that HR of this message is essentially y, or sigma. Okay. And the intuition you should keep in mind here is that if the adversary was able to produce or to give you a list that contains more than one message, then the adversary can also find collisions, because R was not changed. Good. And the error tolerance is going to be inherited from the list decoding, which is R, and the rate is inherited from the list decoding, and the error tolerance, of course, again, is the same as what you would get from the list decoding. So both of them are inherited from the list decoding. And with this, we are done. This concludes our construction. And now I can conclude by stating some open problems and conclusions. So one takeaway from this talk should be that under minimal cryptographic assumptions, without any setup, we are able to construct optimal error correcting codes for PPT adversaries for large constant size alphabet. Okay? And this is strictly better than what's possible for Hamming channels. So if you're interested in codes or giving optimal codes or better codes than what's possible for Hamming channels or for information theoretical adversaries, and you're actually interested in sending information from one place to another or storing information, then it makes sense for you or makes sense for us to consider this relaxation, because this essentially captures all feasible scenarios you can think of. And open problems, well, can we do this for the binary case? Can we extend it for the binary case? And maybe with a stronger kind of assumption or maybe some light setup, but still it would be interesting to get this or equivalent result for binary. And finally, can we get explicit construction for list decodable codes against PPT? Now, list decoding, we know the capacity for list decoding, unlike even the unique decoding case where we don't know the capacity. We know the capacity. However, we don't have explicit construction matching this capacity. So maybe it's an easier problem to do this for PPT adversaries. This is still an open problem, and this potentially could lead to other improvement in other fields or other constructions if this is achieved. So getting a list decode or getting a code that is achieves list decoding for PPT adversaries with optimal capacity that even matches the information theoretical one would be very interesting. And that's all for today.